Hello, in this installment we are going to use our average velocity table and analytical solutions to understand a horizontal acceleration problem. So we have a situation where we have Lucas is running at a steady 2.0 meters per second eastward. So that is what we should recognize as the initial velocity. So that is V0. Experiences an acceleration of 1.0 meters per second westward, so that is the acceleration. And we want to know his displacement after 5 seconds. So that's our time. And the displacement we're looking for is the delta x. So the first thing we're going to do is set up a reference frame. So we'll make this our 0 point. Now, it doesn't actually tell us where he is in this scenario, but we can define this as the positive direction and the negative direction. We're not given an initial position in the first part of the question. So he is running at a steady 2 meters per second eastward. We usually make east positive and west negative. So however it is, he's moving in this direction, and his V0 is a positive 2.0 meters per second. Now he experiences a westward acceleration, so the acceleration is in that direction. And so that makes it a minus 1.0 meters per second squared. Then we want to know what happens after 5 seconds. So we know he is going to slow down as he's going in this direction. He's got a speed of 2 meters per second. He experiences an acceleration. In the negative direction, he's going to slow down. And the question of whether he's able to stop or whether he's able to stop and reverse his direction will remain to be seen in the problem. So let's investigate this with an average velocity table. So we'll start out with 0, 1, 2, 3, 4 seconds. The acceleration throughout is minus 1 meters per second squared. So it's a constant acceleration. Now at the beginning at time 0, we are told his speed is 2 meters per second. Well, we know it's changing by -1 every second. So that means after 1 second, his velocity is 1. And after 2 seconds, it's 0. Aha, so we see that he does actually come to a stop, and we needed 5 seconds. So we want to know where he is after 5 seconds. So 0, and then after another second, his velocity is -1, then -2, then -3. So if the question had asked what will his velocity be at 5 seconds, it would be -3. So we know now his velocity at every instant in time. Next, we will find the average velocity. Now, the mean velocity after no time has passed is meaningless. But if we look at the first second, we can see the average of his speeds is 1.5. And the average for the first 2 seconds would be 1. And the first 3 seconds would be 0.5. And after 2 seconds, we can see it's 0. And after 3 seconds, we can see it's a minus 0.5 because 2 plus a -3 is -1, divided by 2 is -0.5. So we can observe is that the average velocity is decreasing, or is getting closer to 0. It's becoming negative by 0.5 meters per second every second. And so there's a steady decrease of 0.5. Now the displacement, if we will remember, the definition of the average velocity is it's the total distance over the total time. So that displacement is the average velocity times the change in time. So if we take this average velocity and multiply it by the time, it will give us the displacement. So anything times 0 is 0. 1.5 by 1 is 1.5. 2 times 1.0 is 2.0. And 0.5 times 3 is 1.5, and 0 times 4 is 0. And a negative 0.5 times 5 is negative 2.5. So if we were to map this out from the starting point up above, we'd say that's a starting point. And if that's, let's make that the 0 point, his starting point at 0. And in the first second, they've gone 1.5. And in the next one, he's at 2. And the next one, he's back at 1.5. And then he's at 0. And then he's at minus 2.5. So the path looks like this that he took. So what is his displacement after 5 seconds? That becomes a really easy question. It's minus 2.5, or in other words, he is 2.5 meters to the left of where he started. Now, next, we could figure out, we could go on to the second part. And we want to know if he started at 7.5 meters west. That is the x0. So we're saying, whoa, he starts over here. x0 is minus 7.5. Where was he after 7 seconds? So we've figured out displacements for 5. We can go further to find 6 and 7. The acceleration remains the same. The velocity, minus 4 and minus 5, because it's changing by minus 1. And then we have a minus 1.0 and a minus 1.5. And again, how we got that is basically using our average of the velocities formula. And so we have minus 5 plus 2 over 2. It gives us minus 3 over 2, which is negative 1.5. So that's where these numbers come from. They come from the average of the velocities formula, which again, we can only use if the acceleration is constant. It's required of that. So now our displacement, 6 times minus 1 is minus 6, and 1 minus 1.5 times 7 is minus 10.5. So, where was he afterward? Now, where was he? It didn't ask his displacement. Where is the position? Now, we can see his displacement is minus 10.5. So, he started at minus 7.5. So, his displacement is minus 10.5 from that. Now, if we're to use our formula, delta x equals x minus x0, then x is equal to delta x plus x0. And delta x is minus 10.5, and the initial position was minus 7.5. So we have a position of minus 18.0 meters. And that makes sense because he's displaced to the left minus 10.5. Now again, the position is delta x plus xo. And if xo is minus 7.5, then we can figure out the position anytime by adding delta x. Or excuse me, adding xo to delta x. So 0 plus a minus 7.5 is minus 7.5. And if we take a initial position of the delta x, 1.5 plus the initial position, let me write that again up here. X equals delta x plus x0. All we have to do is add the initial position to whatever we have for our displacement. So plus a minus 7.5 gives us 6.0. Minus 6.0. And this becomes minus 5.5. And this becomes minus 6.0 again. And minus 7.5. And this gives us a minus 10. And a minus 13.5. Oh, I made a mistake there. Oh, that is minus 13.5. And minus 7.5 minus is a minus 18.0. So this is a kind of a long way to go through doing calculations, but it allows us to observe everything that's going on. What happened when we changed the starting position to minus 7.5 is we take this entire phenomenon right here and we just shift it over in this direction, 7.5. Now, if we were going to just solve this as a one-off problem and do an analytical solution, the simplest way to do it is to use, since all our questions are about displacements and positions, we just use our position formula. X equals 1/2 at squared plus v0t plus x0. Now, we were asked in the first question, what's a displacement? Well, the displacement is x minus xo. We subtract x0 from both sides, and we have x minus xo is 1/2 at squared plus v0t. Now, of course, x minus xo is the definition of delta x. So then we plug in our numbers. The acceleration is -1, and our initial velocity was +2. So now we have an equation of -1/2 t squared plus 2t is going to give us the delta x. Now this is a model. It's a mathematical model that allows us to answer a question, but it allows us to predict or post-dict particular values. So we wanted to know what happens after 5 seconds. We put in 5, and we get -1/2 of 25 plus 10. And that is -12.5 plus 10, which gives a final answer of -2.5 meters. That is the displacement, and that's what we said our answer was when we used the table. So we could use this formula to plug in and get our answer. Now, if we go to the second question, we want to know where he is, and I will just clear off the work we just did. We now want to know his position when the acceleration is -1, the initial velocity is 2, and the initial position is -7.5. So this is our mathematical model for the motion that will give us the position for any value of time. So we have x is -1/2 times 7 squared plus 2 times 7 minus 7.5. So we have -1/2 of 49 plus 14 minus 7.5. So -1/2 of 49 is -24.5. And 14 minus 7.5 is 6.5. And you can see -24.5 plus 6.5 is -18.0. And that would give us our analytical answer. So that is how we could use an average velocity table to understand what's going on, connect it to our number line, and come up with analytical solutions using our position equation.